Hi everyone, I'm Ritojit Kundu and I'm a PhD student at IIT Kanpur. I am working in the field of theoretical condensed matter physics, and I am one of your TA in this semester in advanced condensed matter physics. So normally you will have two sessions every week, and so one of the session will be on this Saturday 5 to 7 5 p.m. to 7 p.m. and another one will be Monday on so I forget the timing, but you will get a reminder email. So the idea is that we will try to keep this very interactive. So at any point feel free to interrupt me and ask me anything that you are finding difficult. So it will be handy if you keep a pen and paper so that you can also do the calculation along with me, so that you can check with my answer if that is okay or not. And so for today's session, at least what I am trying to focus on is on the week 1's module, which is mostly on second quantization. So normally what I will do is I'll share my screen and I'll write down the discussion so that it will be simple for you to understand. So let me actually try to share my screen and write up all of the things that I am trying to discuss. So yeah, okay, so I think you can see my screen. So for today's session, what I'd like to discuss is so this is week 1 tutorial. So these are the things that I want to discuss. So I want to discuss some Slater determinant states, and how do you actually calculate the expectation value on top of the Slater determinant states. So we'll see after that we'll see some example of second quantized operator. So one thing that I like to do is I like to do a little bit of how does the second quantized operators actually evolve under the time evolve. Okay. And then and if time permits, I would like to calculate some Green's function. And I'll also like to calculate some tide binding, dispersion of tide binding Hamiltonian. So specifically, what I am interested in is in something called Schrieffer-Heeger model, SSH in short. So this is the simplest 1D topological insulator. So this is a model for polyacetylene chain. So which has this topological, which is a topological insulator. And so this is when you write SSH, this is just a very simple toy model, but it actually explains all of this topological feature of this model. So we'll see that we'll try to see what how much you can cover. Okay, so first of all, you already know about Slater determinants. Okay, so for many particle, for when you have more than one particle, more than one fermion, let's say, you will have to consider the many particle states, and you have to properly symmetrize or anti-symmetrize for boson or fermions respectively. So then it becomes a Slater determinant for fermions and a permanent for bosons. So in the lectures you've already seen how to write the Slater determinants. So I'll just try to recap that thing, and on top of that I'll build up. So first of all, for fermions, the Slater determinant is okay. So first of all, let me actually give you two orbitals. So let's call them phi 1, phi 2. So these are single particle orbitals. Okay, and we have two electrons, two fermions. Okay, so and then out of this thing, these two single particle orbitals, we like to calculate what the Slater determinant is. So the Slater determinant, so let's just write this with a psi of 1 and 2. So here there's this 1 and 2, this just means x1 and this means x2. So I'm just simplifying the notation here. So this will be a determinant of a matrix like this. So let me write it as phi 1 of particle 1, phi 1 of particle 2, phi 2 of particle 1, phi 2 of particle 2, and for normalization, because we have two particles, so we have just 1 by square root 2. So we can directly calculate the determinant, which turns out to be something like this: phi 1, 2, phi 2, 1. So 1 by square root 2. Okay, so you can see that directly that if you, so the antisymmetric property of the fermionic wave functions are actually inbuilt into this this state, and you can see that if you just interchange 1 and 2 particles, then the psi will pick up a minus sign. Okay, so which is what you expect for a fermion. Okay, so just to make it a little bit concrete, so let's first try to see an example where you have a fermion. Okay, you have a particle in a box, and you are trying to put a fermion on an energy level. So let's say this is your ground state. Okay, so for ground state, so let's say we are considering only phi 1. Okay, so phi 1 x, which is a ground state, is given by square root 2 by L, which is normalization, and sine pi x by L. Okay, so let's say we are trying to put two particles in the ground state. Okay, so that means we will be using for our phi 1 and phi 2, will be using just our phi 1. Okay, but if you see the previous expression, it is very clear that when the phi 1 and phi 2 become same, then this thing actually becomes 0. Okay, so we cannot put two particles in a single level. Okay, so which is the famous Pauli's exclusion? All right, so we have to consider at least two states. So let's consider the fast excited states also. So phi 2x is square root 2 by L, and sine 2 pi x by L. So if I want to write a Slater determinant for this, then it means that I have to put another particle over here, so which is the E2, and this is the 1 and this is the 2 state. Okay, so the Slater determinant of these two particles will be given by phi 1 phi 2, or just I'll just plug those things in that that formula that you have already seen, 2 by L times sine pi x1 L sine 2 pi x2 L minus sine 2 pi x1 L sine pi x2 L. Okay, so this is a Slater determinant if we are trying to put two particles in the particle in the box. So this is just to give you some a little bit of concrete idea. Okay, so you can do this for many more particles and states. Okay, so this is the same, but so basically if you look at this configuration, so this is the lowest energy possible state if you put two fermions in a particle in the box. Okay, so that means if you just calculate the energy, then this becomes E1 plus E2. Okay, so one particle at E1 and one other particle at E2, so total energy is E1 plus E2. So we'll look at that in a later time. So now let's forget about particle in the box and let's generalize this. Okay, so let's say my state psi, okay, which has this 1 and 2 particles, obviously, is given by this kind of a kit. So you see that in the argument of this orbitals, so these are the number of these are the particles index. So this is particle number 1 and this is particle number 2. All right. So so now we can actually try to calculate any expectation values like we do when we deal with normal quantum mechanics. So in normal quantum mechanics, like what you taught in in your first quantum mechanics course, like at the Griffiths level, you know that if I know a state, okay, then I can calculate any expectation value by just taking the sandwich of that operator between that state. Okay, so that is how we calculate the expectation values. Now so here we are also trying to do that, but here the problem is that this is no more single particle, so we have to modify some of the things, right? So let's say I want to calculate an operator, let's say A, okay, an operator A which acts on particle 1, okay, and it doesn't do anything to the other particle. So I'll write a identity on that. Okay, so this is the mathematically correct way to write this, but you can also write it with A1. Okay, so that also means that acts on particle 1 only, leaves everything else. Okay, so this is what the operator looks like. So what does the meaning of what does this mean is like if I act this a operator on this Slater determinant state, okay, so it actually becomes something like this. So it only acts on objects with which are in it only acts on states of particle 1. So A1 phi 1 1, this is one thing, and then it leaves the phi 2 as it is, minus A 1, phi 2, 1, phi 1, 2. Okay, so you can clearly see how does the a act. Okay, so we can also do similar things for a2. Okay, and this is you can generalize it for n particle state, and the operator is a single particle operator acting on ai. Okay, so by that I mean that, let's say I have an ai and my Slater determinant state is given by 1. So there are many particles, some I comma n, so n number of particles. So out of all of these particles, the ai will directly go to neglect all of these other states, and it will directly act on the I is equal to on aith state, right? So yeah, so that is what will happen. Now I want to calculate expectation values. Okay, so let's say typically what kind of expectation value we'd like to calculate. So let's say energy. Okay, so I want to calculate what is the energy of the first particle. Okay, so if I mean to try to do that, so I have to define the Hamiltonian for particle 1. Okay, so and I would like to calculate the expectation value of that particle. So so this psi 1, 2, this is Slater determinant states h1 acting on psi 1, 2. So I will plug in the form of the psi 1, 2 for the get. I will leave the bra invariant bra as it is, so it becomes something like this: phi 1, phi 2 of particle 2 minus phi 2 of particle 1 and phi 1 of particle 2. Okay, and I have a normalization factor 1 by square root 2. So so now let's act this thing onto these states. So now the principle that we would follow is that this h1 only acts on particle 1. So for example, on this one, okay, and on the second term on this one. So these are the two things that the h act on. So we can directly write it as psi 1, 2, and I'll get E1. Okay, and then I'll get this phi 1, 1, phi 2, 2 minus phi. Okay, so then on the second term, this h will act on only this one, so that will give me an E2. Phi 2, 1, phi 1, 2. Okay, so and on top of that I have a 1 by square root 2. So you can see that okay, so before that you can see that I can plug in the bra side of the state also. So this becomes phi 1, 1, phi 2, 2 minus phi 2, 1 and phi 1, 2, right? And also I have a 1 by square root 2 factor, 1 by square root 2 normalization factor for this case as well. So you see 1 by square root 2 from here also I'll absorb in this, and it becomes 1/2. Okay, so so this is the first part, and then we have this another part E1 phi 1, 1 phi 2, 2 minus E2 phi 2, 1 and phi 1, 2. Okay, so here I like to remind you that these orbitals are actually orthogonal. So phi I, phi j is actually 1. Okay, so it is actually delta ij. Yeah. So let's actually look at this inner product term by term. So this will act on this, and the phi 1 and phi 1 will give me 1, and along with phi 2 will also give me 1. But when this this thing will act on this, then I'll have a phi 2 and phi 1, but because these are orthonormal, then this will become 0, right? So from that similar argument, you see that if I have this thing acting on this thing, I will get a 0 because phi 1 and phi 2 are orthonormal, whereas this thing, when I'll act it on this one, I'll get a something non-zero. Okay, so let me just right away write what is the energy of this first particle is. So it is just E1 plus E2 by 2. Okay, similarly I can also try to calculate the energy for the second particle, so which is something like this: H2 psi 1 2. Okay, so this is the energy of the second particle. So, and you will see that this will be nothing but again E1 plus E2. So so in a sense, if you like to calculate the total energy of the particle, so it becomes H of 1 plus H of 2 sandwiched between the bra and kit of this later determinant states. Okay, so this is just E1 plus E2. Okay, so this is not a surprise because if we think about the physical picture behind this thing, we'll see that if we have two states with energy 1 and energy 2, so there are only two possible combinations that we can put our particle in. So one combination, I can put my particle 1 here and particle 2 here. Okay, so in that case my energy will be something like E1 plus E2, but this is not the only case. The another combination is I can put my 1 here and 2 here. Okay, so that in a sense that if you just take an average over all of these possible combinations, you will see that just from these physical arguments, you will see that this will become just E1 plus E2 by 2. Okay, plus just E1 plus E2. Okay, so the this calculations might look daunting, but I mean you can also try to check with your answer by some physical arguments, right? So yeah. So now normally when we have any kind of single particle operators, so for example something like this, so let's say I have a single particle operator just AI, okay, and I am trying to calculate some n particle states. So these are Slater determinants, Shi's are Slater determinants. So what will happen is this will just become the Shi I, okay, AI Shi I, so just that, it will just become that. I mean so single particle expectations are really easy. Now if you want to calculate something like this, let's say you have some B which is a sum over this A of I, so you can clearly see that the expectation value of B on this later determinants, it will be just a summation over all of this Shi I, A I, Shi I. So in that case you can also remove the A's I index, so you will basically compute the expectation values of the A on each of the states. Okay, so from here also you can see that the Hamiltonian, so from here, so let's calculate the Hamiltonian's expectation from this kind of formula. So we see that this will be just Shi 1 Hamiltonian, so H Shi 1 plus Shi 2 Hamiltonian Shi 2. Okay, so you can say that this is just E1 plus E2 like we have already obtained. Okay, so now this is all the story about single particle operators. You can generalize this to two particle operators. For example, you can have some operator C which is something like Aij. So I and J are two particle indices, and I greater than J removes the double counting. So you can take that, and you can also reduce this kind. You can also reduce this kind of formula. For two particle, the calculation is slightly involved than the single particle one, but you can try to do that. So this is what you get when you have these slated determinants. But so what I'm trying to emphasize, I mean, I'm just trying to show you that the calculations using slated determinant can be really daunting, and this can be really messy kind of calculation. So which actually inspires us to take an approximation of this go to the second quantized representation. So this is how I'm trying to motivate the second quantization, right? So so I can so let me just finally do one thing. So let's say I have bosons. So bosons, so we have to symmetrize the wave function. So unlike fermions, we write a Slater determinant. Here we will write a permanent. Okay, so I mean, you know, how does it work out? So let me actually give you an example of how does the state look for three bosons. So I have three bosons. Okay, and so I am putting it like something like 2 in ground state and 1 in excited, fast excited. So for boson, there is no Pauli exclusion principle, right? So two electrons can actually live in the same state. Okay, so what I will do now is, so let me write out the psi. So B for boson. So 1, 2, 3. So let me just write it like that. So okay, so let's also draw a energy diagram, so which tells me that okay, two particles are in ground state and one is in the excited state. So I can have orbitals. So one is for ground state, so particle 1, phi 1, particle 2, and phi 2, particle 3. Okay, so this term means that, so I have particle 1 and 2 in the ground state and 3 in the excited state. All right, and so this is not a single combination, we'll have some other. So phi 1, 1, phi 2 of 2, and phi 1 of 3. So that means that, so particle 1 and 3 are in ground state and 2 is in excited state. So what other combinations we can have? So we can have one more combination. So where this first term is phi 2 of 1, phi 1 of 2, and phi 1 of 3. So this means that, so particle 2 and 3 is ground state and 1 is in the upper state. Okay, so I mean, you have got the full thing, but still there is the normalization that you will need. So you have this 1 by square root 3 normalization. So for n number of particles, so you have normalization 1 by square root n. Okay, so in that way we have square root 1 by 3 for 3 particles and square root 1 by half for 2 fermions that we have seen before. Okay, so similarly, using these states, you can calculate your calculate all of the quantities that you want to calculate, taking just expectation values on some average onto these states. Okay, so these are like really difficult calculations to keep track of all of these permutation combinations. So that's why this second quantization was introduced, just to avoid these kind of things, but it still but still keep all of the property of fermions, the antisymmetric or symmetric property of fermions or bosons. Okay, so let's talk a little bit about the second quantization, right? All right, so so second quantization, first of all, I'd like to just tell you, second quantization is a misnomer. So we are not actually quantizing anything, rather it is just a trick to I mean, it is just a different kind of representation that that we are using here. Okay, so what do I mean by that? So for example, let's take back our previous example, where we have one particle in the ground state, one particle in the excited state, and the other rest of the levels, let's say, are zero. These are not filled. Okay, so how do I write that? So I showed you that we can write it with this later determinant, so which is something like just phi 1 1 phi 2 2 minus phi 2 1 phi 1 2. Okay, so this is later determinant. Okay, but so there is one another way that we can describe this kind of a state, which is like which is called the occupation representation, occupation number representation. So in occupation number, what we do is, so we'll like list out all of the number of particles which are present in a certain state. So it is like, so there are some placeholders. So I mean, this is what number of particles are in the first ground state, in second state, third state, fourth state. So for this kind of configuration, so we'll just plug in 1 and 1 in this first two places. So that corresponds for one particle in ground state and another particle in first excited state, that you can see here. And on top of that, rest of these levels are actually zeros. Okay, so this is, we are representing the same state, but which is like which is now our prescription is actually different. Our description is actually a little bit different. So when you do that, so there is an interesting thing that you can do. So you can actually use some abstract kind of operators, which are something like this. So let me write this down: C1 dagger and C2 dagger. Okay, so what the C1 and C2 does is that it actually creates a particle on state I. On first state, first level, let's say, and this creates a particle in the second level, and so on and so forth. So there is a short way of writing this. So this is C1 dagger, C2 dagger acting on 0. Okay, so this 0 is sometime called a vacuum. So vacuum, because so the 0 here means that there are no particles in that state. Now so let's appreciate for a moment that we initially started with this kind of a huge object, this kind of very hard to deal object, and by changing our way of describing the same state, we have actually obtained a very simple prescription in terms of a very simple looking object, very simple object like this. So these are called creation operators, and as I mentioned, these will create a particle on level 1 and a particle on level 2 on 0. Okay, so now when you write a state like that, so we say that okay, we are writing the state in a second quantized representation. So now we can ask the questions that whether it has all of the symmetry properties, it still obeys the Pauli exclusion principle or not. So actually it does. So so how do you see that? So this this creation annihilation operators has their own set of commutation anti-commutation relations. So let me actually list down some of these things. So let's say we have some Ci Cj anti-commutation. This will give you delta Ij. So if these are fermions. So we are specifically talking about, for now, spinless fermions, and you can write down all other possible anti-commutators as well, so like Ci dagger, Cj dagger, which will be 0, and then you can write Ci Cj, okay, which is also 0. So these are the three anti-commutation relations that you can write. So let's see that whether this is actually gives us a minus or not. So the state that we are describing was something like this: C1 dagger, C2 dagger, okay, acting on 0. So we are trying to interchange the 1 and 2. So how do I do that? So we can actually just exchange these two. So when you do that, this formula will tell us that I will pick up an additional minus. Okay, so this is okay. So let's do it a little bit systematically. So I need to exchange 1 and 2. Okay, so C2 dagger, C1 dagger, 0. And this anti-commutation relation actually tells me that I can do that, but I mean I can use that. I can actually again reverse it back, but with a cost of a minus sign. So this becomes so like when you do this exchange of 1 2, so you see that we get actually minus chi, so which is what we would like to have for fermions, right? So we see that this annihilation operators actually obey the antisymmetric property, and on top of that we want to see that this also obeys the Pauli's exclusion, right? So now let's say I want to have a chi where I have C1 dagger, C1 dagger. So I want to keep I want to create two particles on a single level 1. Okay, so what does the anti-commutation relation tells me about it? So it tells me that, so if I write the C1 dagger, C1 dagger, C1 dagger, so I can actually flip these two C1 C2s back, and that will give me an additional minus C1 dagger, C1 dagger. So I can actually bring this onto the other side, then I'll have 2 C1 dagger, C1 dagger is equal to 0, C1 dagger, C1 dagger is equal to 0. Okay, so this is so what we get. So that means now chi, so I can actually plug in this 0 here, so 0, so I cannot have any state which has two particles in single level. So that is what Pauli exclusion principle is. Okay, and this is how we get the antisymmetry, how we verify the antisymmetry. All right, so now we know we know what the this anti-commutation relation looks like for fermions. So let us also write down the this anti-commutation relations for bosons only. So boson. So for boson, the relations are exactly same as before as fermions, but here we just need to modify a little bit of this. So we have to replace the anti-commutators with commutators. Okay, so that actually gives us commutation relation from boson. So one important thing that you have to notice that for fermions, so we have anti-commutators, and for boson, which we have commutators. Okay, so commutators are actually so these are so I mean, this actually gives you the property that bosons, when you exchange them, the wave function doesn't pick up a sign. Okay, so that is what that is what this creation this computation algebra looks like. And when you know the algebra of this fermions and of this fermions and bosons, you can basically form any kind of you can basically find all of the properties of this bosonic or fermionic, any bosonic or any fermionic operators. Okay, so Now I have not been talking about spins, but for spins, if you add spins, then it doesn't change much. So let's talk about spinful fermions. So for spinful fermions, I will use the similar kind of notation: Ci sigma, comma Cj sigma prime. So here the sigmas are, they stand for up and down spin. Okay, so this is nothing but delta ij times delta sigma prime. Okay, so the other relations also follow similarly as before. Okay, so these are all of the anti-commutation relations with sigma prime. So just note that this ij part doesn't change, so it only introduces another sigma prime. Okay, so it will have many more other other Kronecker deltas if you will add some other indexes also. Okay, some other color, other flavor of this fermions, but let's keep it simple. And for bosons also the same thing happens, but but again you have to replace the anti-commutators with commutators. Okay, so yeah, so these are the things. So now when you know all of the anti-commutations, we can actually, so these things are known as the anti-commutation algebra. Okay, so when we know these things, we can actually calculate, simplify this commutator or anti-commutator relations. So for that, let me introduce to you some very useful identities. So for example, you will see that many times you will have this kind of a commutator. Okay, so the commutator, you can simplify it, it becomes something like a bc's commutator plus a c's commutator times b. Okay, so how do you prove that? So to prove that, you first expand out the commutator, so it becomes abc minus cab, right? So now you can actually now you can actually plug something in. So abc, let's say minus acb. So now because I'm putting something by hand, I'll also have to subtract it, right? So the subtraction of acb is actually needed. So yeah, actually plus acb is needed minus cab. So now from these two, first two, you can see that I can take a common. Okay, and then I am left with b and c's commutator, right? And for the next term, I can take b out, and then I will have a and c's commutator. Okay, so now you'll see that this is useful for bosonic operators. Okay, because bosons have commutation relations, unlike fermions which has anti-commutation. But we can also I mean simplify this thing so that anti-commutators appear instead of commutators. So this is the first relation that that will be useful for us, and this is the second relation which is given by some anti-commutators. A times bc is anti-commutator minus a times c is anti-commutators plus b. So which is again you can prove in a similar fashion. So first expand out the commutator. Okay, and again we'll just add and subtract something. So which for this case will be something like acb. We'll have to subtract that out also. acb minus cab. Okay, so now this becomes a and b c is anti-commutator minus a c is anti-commutator times b. Okay, so this is you can see that anti-commutators appear here in this expression. So this will be useful for fermions. Okay, so I mean these are two very handy kind of commutators. So we'll be using them later in today's session. So yeah, so before that, so let me actually show you how do you calculate second quantized operators from first quantized operators. So normally we see that the operators are given I mean many particle operator is given in terms of a summation of single particle operators uh, j I. Okay, so let's this is small ji. Okay, so here so this is called a first quantized operator. And this actually acts on Slater determinant states. But what we want to have is that so because we are already writing in place of Slater determinant the second quantized operator, so we'd also like to find a representation for second quantization. So we've already done this in the so Professor Basu has already shown in his lectures. So let me just recap that. Okay, so if I just write the final result, so the second quantized representation, so it is just this. So you will take the single particle part from this summation, which is small j, and you take a matrix find the matrix element of this. Okay, and along with the CR dagger and CS. So here the R and the S are some quantum numbers. Okay, so it can be momentum, it can be spin or anything, and the CS and CR dagger are the annihilation on of that S level and the creation of the R level respectively. Okay, so this is what this second quantized operator is. Okay, so now it is also very important to know this representation in terms of field operators, because that will be used a lot in this course. So to do that, so let me actually first define what a field operator is. So field operator is actually an abstract operator that lives in a many body Hilbert space, or called the Fock space, so which is given by this kind of a relation. So here the k can be any quantum number, it can be momentum, it can be spin or anything, and the is, so let me actually annotate all of these things, different parts of this expression. These are wave functions. So wave function, so solution of the Schrodinger equation by plugging the Hamiltonian of whatever problem you are trying to do. So this is an annihilation at k level. Okay, and so this is the field operator. This might look complicated, but what it does is very simple. So this actually annihilates a particle at x. Okay, so you can think of that. Okay, you have some particle, okay, some x somewhere here, and some particle is sitting here. Okay, and what happens is when you actually hit this particle with this psi, it actually goes away, it vanishes. So that is what the psi does. Now when I've defined psi, then it actually comes with another operator which is called the Shy dagger. So Shy dagger, you can just conjugate the above expression to get the expression for Shy dagger. Okay, and so this doesn't annihilate. This actually creates a particle at position x. Okay, so so I can actually introduce. So let me show you how do we get field operators in the expression of this kind of single particle operator, right? So I can introduce a resolution of identity here. So which is written in the positions basis. So then this becomes j of x, this becomes x and s, cr dagger cs. Okay, so now from your quantum mechanics course, you know that this is psi r at x and this is psi psi s of x, and there is a dagger sitting here. Okay, and this is the jx. So you can see, okay, so that is what you got. So now if I can pair this with this and I can pair with this with this, I can see, and I can do the r and s summation, and from the definition of the field operator I can actually replace those summations with the with the field operators like this. Okay, so this is the second quantized representation. Of j. Okay, so here I have not shown you how do you go from this step to this, because the derivation is not actually few lines derivation, it is a long derivation. But so I am just giving you the final expression of what you get after doing this, all of these things. Okay, so the main thing that I would like to highlight here is, so I mean, if you want to take something from this part of this session, so just remember that this is actually an important object. Okay, and also so let me actually put a star here, and also this is a very important relation that will be handy. Okay, so let's actually try to see try to use this principle and try to find some second quantized representation of some operators. Okay, so first one is, let's say, kinetic energy. So kinetic energy is given by something like this. So the I is number of particle that goes from 1 to n, and then there is pi square to m, right? So now I want to write a second quantized representation of this. So how do I do that? So from here I'll actually take the single particle part, so which is just p square by 2m. So as you see that I'm not writing any I index here, because as I mentioned that this is a single particle part of this many body operator. Okay, many body, so but still this is still single particle, but I mean you get the point. So you just remember that I index and use the rest of the part. So that is what it means. Okay, so and on top of that I'd like to take an matrix element between these two momentum eigenstates. Okay, so and as I have shown you before, that this will come with this creation ck prime and annihilation at ck, and there is summation on k prime and k. Okay, so So these are momentum eigenstates, k's are. So you know that p, which is a momentum operator, when that acts on this momentum eigenstates, so it gives it becomes just the eigenvalue equation as this. Okay. And so these are eigenvalue equations from Cayley-Hamilton theorem. You can see that this will be true for any polynomial. So if I raise p to square, then it becomes just k square. Okay, so which we will do here. So here what I'll do is I'll just take p square out, so it becomes k square by 2m. This is ck prime dagger ck. All right. Now remember that this k and k prime are actually orthogonal. So this is like delta k and k prime. Okay, so I'll plug that in. And I'll do a summation over let's say the k prime, and because of the Kronecker delta, only when k prime will be same as k, then I'll have a non-zero contribution. Okay, so I'll just write this down. So this k prime also becomes k. Okay, so now this is my second quantized representation of the kinetic energy operator. Okay, so now this is what you have already seen in the lectures. So I want to go beyond this, and for that, so I'll like to take the example. I'll like to take study the operator which is called a charge density operator. Excuse me. So what does it physically mean? So charge density operator is written by rho of x. So now if I'm looking in a material, in some object, so there will be many electrons, right? So there will be scattering of each other, or and so on and so forth. Okay, so they are moving all over the place. So now what do I ask is that if I look at a certain position x, so for example, let's say this is my x. So I am drawing a unit cube around that point position x, and I am asking what are the number of charges. What is the charge in this unit cube? Okay, so that will tell me which is that will tell me the charge density of the system. Okay, so now, okay, these are the logic that we are going to develop our charge density operator from. So but how do we write it in terms of mathematical expressions, right? So in mathematical expressions, we'll write this as a summation over I, and all of the electrons has charge minus E, and I am to count how many particles are there in the box. Okay, so why do I want to count it? So let's say I have one, so let me index all of these particles. Okay, so now I know all of the position. Let's say I know all of the position of all of the particles at all of the time. Okay, so now I'll be iterating through all of the particles. Okay, and I'll see, okay, if I let's see whether the particle 1 is in position x, let's say whether particle 2 is in position x, 3 is position x, or in whichever particle in position x. So I'd like to count all of the number of particles which is at position x. So how do I do this counting in terms of how do I write this number of this counting? So this is nothing but xi. Okay, so here xi is the operator which is a position operator. So for the ith particle, right? So I have I summation from 1 to n. So these are number of particles. Okay, so now I want to find a second quantized representation of this charge density operator. Okay, so now for this thing, what will be handy is something like this. This expression will be handy. So we'll directly plug in this. Okay, and we'll just use the function j of x. So let's see how to do that. So second quantized representation is written by, so here I'll be using a dummy variable y, because I already have a free variable x sitting outside of the expression. Okay, so yeah, you have to be careful, a little bit careful while doing this. So e, then okay, so now let me put this shy dagger first. Shy. Okay, so these are shy dagger, and in between I have to sandwich something. So I have to sandwich the single particle part from this summation above. Okay, so which is nothing but delta x minus y. Okay, let's say y minus x, something like that. So now you know the properties of the Dirac delta. So Dirac delta, or let's say it's just delta x. So is 0 if x not is equal to 0, and is infinity if x is equal to 0. Okay, so in that way, so we can do this integration fairly simply. So it becomes psi x and it becomes psi of x. Okay, so this is how the density operator looks like in second quantization. It is just the field operators, psi dagger psi. Okay, so until now I have not been talking about spinful spins in the field operators, right? But we can actually introduce spin operators. So let's actually do that. For spin hop, psi is actually spinor field. Okay, so as you know, if you want to describe spins, the internal degree of freedom of spin is 2. So field operators also become like it's a 2 spinor. Okay, excuse me. Then the field operator, I'll have to write it as a column vector, so which will be something like psi up x and psi down x. Okay, so now if I want to calculate rho x of this spinful objects, so what I will have is, I have this psi dagger x, psi down dagger x, psi up x, psi down x. Okay, and you can multiply this. So let's do on the next page. So you can multiply this and you will see that you will get something like this. Okay, so clearly okay, so there is so I missed a minus e factor. So clearly you see that this actually decouples into densities of upspin plus densities of downspin. Okay, so this is the final answer for your charge density. Okay, so similarly, so charge density is really an important quantity, which will be important when you'll be when you'll do linear response. Okay, and so there are also other important operators which are for example spin density. Okay, so spin density is again, so we'll again start from that nice physical picture that we had. So we have some system, okay, and there are many particles, and we're asking that at position x in that unit cube, what is the number of total spin in that thing. Okay, so that will define the spin density. So similarly, from this physical intuition, I'll be writing the spin density operator. Okay, so the spin density in this case will be given by sigma I, so spin of the ith particle, okay, spin operator, and times delta x minus xi. So xi is the position of the ith particle, and there is a summation of I. Okay, So here also you can do the similar thing that you have done before. So for example, what we will do here is we'll use the field operator kind of representation of this operator, and we'll directly write it as, so dy, because x is a free variable on the left hand side, so shy y dagger shy y. So in the single particle part we'll just plug in sigma I. Okay, so not even this anymore, not I'll not put any I index. Okay, so this, so yeah, and also there is this delta x minus y. Okay, so now you get shy dagger x sigma operator and shy x. All right, so now so I mean this is a vector, this is also a vector. So you can use like this representation, something like this: shy up dagger x, shy down dagger x, and then there is a sigma matrix sitting here, and then shy up x, shy down x. So these are capital shies for field operator. Now if you choose components, something like sx, okay, so then what you will have is you will have the similar thing, but the sigma will be replaced by a Pauli x matrix. So it will be Pauli x, and let me actually write the Pauli matrix itself: 0 1 1 0. So this is shy up dagger x, shy down x plus shy down dagger x, shy up x. Okay, so this is my sx operator, sx at position x. Similarly you can calculate sy operator, so which will be, so I'll directly write this result, which you can verify. And similarly sz operator also. So these are the three operators, three spin operators that you will have. This is three second quantized representation. Okay, so another important operator is something called a current density. So current density operator is written by J, which is also a vector. So there is sum over all of the particles and the current carried by each of the particles. So if you just write E times Vi, that is what a current carries, that is what a particle carries current in a unit time. Okay, so delta x minus xi. Okay, so normally this Vi is given by P by M. Okay, and if you have additional electric or electromagnetic field, then this Pi becomes Pi plus some Ea. Okay, Xi. So and then there are all of these details that you can work into. And one thing which is important, that because Vi has momentum, and we are trying to write a object, a function and an operator which is a multiplication of both momentum and x, so one needs to symmetrize it to use it. Okay, so you can symmetrize it and use this thing. So I'll give you the reference from where you can actually work out all of these things. So this is the reference called Giuliani. So let me not mess up the spelling. And Vignale. So in the appendix 2, I mean that is actually really a gem, and all of these things are actually calculated in those appendix. All of these many different operators and their representations. They also show what happens in momentum space. How does the operator's second quantized operator looks in momentum space? Okay. Okay, so this is a lot of second quantized operator that I have shown you. Now let's actually talk on some different things. Talk about some different things. So let's talk about how to diagonalize a second quantized Hamiltonian. Okay, so let me give you a simple Hamiltonian. For example, let me give you something like epsilon c2 dagger c2 minus epsilon c1 dagger c1. Okay, so this kind of Hamiltonian is called a diagonal Hamiltonian. So I mean, if you have terms like ci dagger, ci dagger ci, I mean, if these both of these indices are same, so then you call this to be diagonal Hamiltonian. So which becomes actually clear, the naming becomes clear. So if you write this thing in a matrix form, so which you can do by writing this thing like this. So c1 dagger, c2 dagger, epsilon 0 0 and minus epsilon. So we see that this is what I mean if you write this in the matrix in a basis or in the matrix representation, so this is what the matrix is, and we can clearly see that this is actually sitting at the diagonal. So the eigenvalues of h at this h are really epsilon and minus epsilon. So that means we have actually two levels. So one has minus epsilon energy and another has epsilon energy. Okay, so now let me actually add something more to the Hamiltonian, some off diagonal terms. So this is what we had originally. Now I am putting another term in the off diagonal. Okay, so now if you again write the matrix form, so you'll see that it becomes something like this. Okay, so now one has to find the eigenvalues of this Hamiltonian matrix. So it actually becomes very simple for 2 cross 2, because 2 cross 2 we know that any matrix you can write in terms of Pauli matrices. So Pauli matrix actually forms a basis for 2 cross 2 matrices. Okay, so you separate out the diagonal and off diagonal terms. Okay, and you see that the first term is nothing but epsilon sigma z. The second term is delta sigma x, right? So as soon as you have actually decomposed this thing in Pauli matrices, you can find the eigenvalues of this Hamiltonian, right? So the eigenvalues are nothing but epsilon square plus delta square plus minus. Okay, so now let's see what happened actually. So we initially had two energy levels, minus epsilon and epsilon, and after adding a off diagonal term, it has actually become minus epsilon square plus delta square and epsilon square plus delta square. Okay, so that is what it is. Okay, so Yeah. So I mean, this is, I mean, as simple as how, I mean, you can calculate the eigenvalues. So it can become difficult. I mean, it can have a lot many terms in the Hamiltonian, but this is the basic formula. You first write it in the matrix form. You form this matrix and you put it in a computer, in some linear algebra program that can solve the eigenvalues. So that is what people normally do. Okay. So so let's move on. So now, so we have been talking about a lot about all of these operators, right? All of second quantized operators. But what we have not talked about is how do they evolve in time. Okay, so this is an important topic that we need to talk about. So this is time evolution. Okay, so time evolution is so for any operator, the time evolution operator is governed by this Heisenberg's equation of motion. So this term is actually there when O has explicit time dependence. Okay, so okay, so but normally whatever case we'll deal with, that this term is not actually there, so we'll just ignore about it. And the Hamiltonian is the total Hamiltonian of the system. So let me actually give you let's first mention what the Hamiltonian is. So to start with, let's write a Hamiltonian. So it is some diagonal Hamiltonian, okay, and alpha is some quantum number. We don't have to know the quantum number, I mean which quantum number it is, but some, let's say, quantum number. Okay, now I want to find out how does the C alpha t evolves. I mean, what is the time dependence of C alpha t. Okay, so to do that, I'll again plug this thing in the Heisenberg's equation of motion. So I'll put something like this: C alpha t is equal to C alpha t and Hamiltonian's commutation. Okay, so the Hamiltonian is a summation of this kind of terms. So you see that I'm using a beta here because the alpha is already being used as a free index, and in this expression the alphas are just dummy index, so I can change alpha to beta, right? So I can actually extract out the summation beta. So I'll get something like this: C alpha t, C beta dagger, C beta. So let me actually flip that commutator with the cost of a minus sign. Okay, so now you remember, so the identity that I told you about in the beginning. So if you have some operator, some commutation like this, so it becomes actually a simple and anti-commutation relation like this. Okay, so let's just use that, and we just mention that, okay, these are the ABC operators. Okay, beta epsilon beta. So let's break that commutator. So we have C beta dagger, C beta, C alpha. So actually all of this should have this T argument. Okay, and minus C beta dagger, C alpha t, and C beta t. So because all of the this anti-commutation of annihilation operators vanish, so this is 0, and this will give us a Kronecker delta alpha beta. So let's just simplify this thing. So because of the Kronecker delta, I can do the summation over beta, and I'll get epsilon alpha C alpha T. Okay. So this is just I C alpha T dot. Okay. So now, I mean, the task is to calculate this the solution of this ordinary differential equation. So you can check that the solution of this expression is this ODE is minus I epsilon alpha T C alpha 0. Okay, so it's just that. So once we know the annihilation time evolution of the annihilation operator, we can calculate the time evolution of the creation operator as well in the similar way, but we can just take the dagger of this expression and we can find the annihilation operator. So you see that for the annihilation operator in the exponent we have a plus, okay, and for the creation we have a minus, right? And so I'm not mentioning it, but I am actually using a dimension where h bar is equal to 1. Okay, so in that unit I am working, so just to get rid of the hassle of using h bar everywhere. Okay, so this is one of the way to find the time evolution. But there is another way. Okay, so the another way is to write down the formal solution of this expression. So formal solution is O of t is given by ut dagger O ut, whereas these uts are evolution operator given by exponential minus I Hamiltonian times t. Okay, so we can use that. So if we use that, what we'll get is so we'll have C alpha t is u t dagger C alpha ut, so it is e to the power iht C alpha e to the power minus iht. Okay, so you will see that this kind of thing actually appears in many places in quantum mechanics. And to simplify this, there is a special formula called BCH formula, so Baker, Campbell and Hausdorff formula, which is given by something like this. It is y plus commutators with nested commutators with y. And so on and so forth. Okay, so we can plug that in right away. So what we'll have is we'll have something like this. So we'll have C alpha plus C alpha commutator with H plus C alpha. Okay, so I'm actually writing the other way. So H C alpha H C alpha 1 by 2 factorial and so on and so forth. So if you'll calculate this H C alpha which we did little ago, you will see that this is nothing but so I am missing some factors of I t, so I t square and so on so forth. So you will see that this will become minus epsilon alpha C alpha. Okay, so if you do that, plug that thing in, you will find that it is nothing but epsilon alpha C alpha plus I t whole square by 2 factorial epsilon alpha square C alpha and so on and so forth. Okay, so I think this is a minus. Yeah, probably this is okay. So if you just resum this Taylor series, you will see that it is nothing but it is a minus I epsilon alpha t. Okay, so now you can I mean you can also do this for the creation operator. Okay, so this is one very important formula which is called the BCH, Baker Campbell Hausdorff formula. Okay, so uh, I actually want to calculate some simple Green's function. So let's actually do that. So again, we'll be using the similar Hamiltonian. So excuse me. Okay, so we'll learn more about Green's function as the course goes on. But so basically, if you want to define a Green's function, so the Green's function, so this is called a retarded Green's function, and so you will know why is it called a retarded Green's function soon. So this is given by minus I theta t. Okay, so what does this expression mean is that, so let's say you have uh, some okay, so let's say so you are creating you are annihilating at time 0, and again you are creating at time later time t. Okay, so what does that mean is that so you first annihilate and then you are creating at time t. So this is what the Green's function means. So this is the amplitude of this process. So so we were looking at a non-interacting Green's function, for which case it is actually very simple, and the Hamiltonian for which we are trying to find the Green's function is given by the same that we looked before, epsilon alpha c alpha dagger c alpha. Okay, so this is the Hamiltonian, and as soon as I have mentioned the Hamiltonian, so we know all of the time evolution, right? And let's actually try to simplify this thing. So we know that c alpha t is given by e to the power minus e alpha t c alpha. Okay, so we'll plug this thing back into the expression of the retarded Green's function. uh, so let me just mention gr theta t, and then I'll have c alpha dagger, and I'll actually extract out one of this minus I epsilon alpha t. Okay, and we see that this is actually the anti-commutation relation, and we will just use we'll just directly plug that one, this I epsilon alpha t. Okay, so now so this is the Green's function in time space. Okay, so but normally in practice what we do is we always go to frequency space, and we observe I mean frequency space it looks somewhat simpler. Okay, and it is more natural to look into frequency space. So to do that we'll do a Fourier transform to frequency space. So the formula for Fourier transform is given by this. So the omega is our frequency, and we have to perform integration. So this is the Fourier transform of g retarded alpha t. Okay, so I'll just plug minus I theta t e to the 1 minus I epsilon alpha t. So because of the theta t, so theta t here is a heaviside theta function. So it is like 1 beyond 0. Okay, when the argument is positive, then it picks up to 1, which is, this is also called a step function. So this will restrict the integration from 0 to positive infinity. Okay, so I actually I missed this factor of e to the power I omega t, e to the power I omega t. So moreover, so I mean, what we get is I omega minus epsilon alpha t dt. Okay, so we'd like to add a convergence factor, because you see that this is a highly oscillating expression, and normally what people do is, people to find a solution, I mean, to integrate this, people actually add a convergence factor, some I delta, okay, t dt. Delta. So this ensures that at t infinity this doesn't this becomes a 0. Okay, so when you do this integration, so this becomes e to the power I omega minus epsilon alpha plus I delta, and in the denominator you have minus epsilon alpha plus I delta, and this the integration limits are 0 to infinity. So at infinity it is I factor in infinity it is 0 because of the convergence factor. So delta is actually a very small positive number. So in infinity it is 0. So 0 minus 1 by I omega minus epsilon alpha plus I delta. Okay, so it is nothing but, so this is g alpha retarded function of omega. So when you know the Green's function, so you can actually find a great deal of information of the system. So this Green's function actually encapsulates all of the information of the system. Okay, so this is how the Green's function looks like. So let's see what else I wanted to talk about. Yeah, so now you see that the alpha here, I have not mentioned what alpha is. So alpha can be k. Okay, so in that case the Hamiltonian is let's say is given in the momentum space by something like this. Okay, and then so this is a Hamiltonian of a single band. So CKs are accretion and annihilation operators in the momentum space. So it creates a electron at momentum k or destroys at momentum k. Okay, so so in that case you can actually find out how the Green's function is, and this is related to your assignment problem in and week 2's assignment. So g k omega is given by 1 by omega minus epsilon k plus I delta. Okay, so yeah, so that's your Green's function for a block Hamiltonian, if you like. Okay, so this is Green's function, and so let's actually talk about the last thing that I want to talk about, which is let's talk a little bit about tight binding Hamiltonian. Okay, so you all know what tight binding Hamiltonian is. Okay, so let's recap some of the things about tight binding model. So let's say I have a chain of atoms in 1D. Okay, and there is hopping between the nearest neighbors. Okay, and the hopping is given by the t. So for this, the Hamiltonian that we'll write is given by t c I dagger c I plus 1. So let's say we only allow the nearest neighbor hopping. Okay, and there is no other hopping, so we'll put just the Hermitian conjugate part as well. Okay, so now what we want to do is we want to make this thing periodic. So by connecting its end, so it is like a circle, so it is n periodic. So after n of these sites, it actually comes back to 1. Okay, so that is what it means, n periodic. And then I can actually go to momentum space. So here I like to show you how do people go to momentum space. So for that you will define this operators as this. So let's write this as j. So e to the power I k j c k, and similarly the annihilation, the creation operator is also written by its conjugation k e to the power I k j and c k. Yeah, c k dagger. So ck they also obey this anti-commutation relations, as is cj's obeys anti-commutation relations. So let me just write that down. C J C L. So these are in real space. So this is delta JL. Similarly, C K C Q. This is delta KQ. Okay, so let's do the Fourier transform and see what do we get. So Hamiltonian is given by summation over J, and there is a T, and I'll plug in these transformations, and those there will be two summations, so I'll be calling them K1 and K2. So the first one is given by minus I K1 J, and the second phase factor will be given by I K2 J plus 1. Then we will have C K1 dagger C K2 and Hermitian conjugate. So let's arrange these things and see what do we left with. J K1 K2 e to the power I K2 minus K1 J e to the power I K2 C K1 dagger C K2. Okay, so now we can actually use this nice relation, I mean, which is again another definition of a Kronecker delta. So this will give us delta K1 K2. Okay, so we'll use that here. So T K1 K2 delta K1 K2 divided by K2 C K1 dagger C K2. So yeah, so okay, so I'll just do the summation over K1, and I'll call the rest K2 to be K. Okay, so I'll just do this e to the power K C K dagger C K plus Hermitian conjugate. So if you will just put all of these things, so you will get e to the power ik, and it is a minus ik for the Hermitian conjugate part. So this thing is nothing but 2 times cosine k. So this is this is the band. This is the band of this chain. So you can plot the dispersion. So the dispersion looks something like this. So this is minus pi to pi. So this is in the middle. This is something like that. So this height is given by 2t, and this is also given minus 2t. Okay, so the bandwidth is actually 4 times t. Okay, so this is I mean, this is how you normally calculate the momentum space representation of a Hamiltonian or some block Hamiltonian. So with this, I actually wanted to talk to you about something called a something called SSH model. Okay, so in this previous model that I showed you, there are only single atoms in a unit cell. So like this is a unit cell, this is a unit cell, something like that. Now SSH is a model which has got two unit cells. I mean, two atoms in a unit cell. So let's just draw that. And another will be given by blue. Yeah. So for example, so this is one unit cell. Okay. And so on. So now when you have this kind of unit cell structure, so this is basically a polyacetylene chain. Okay, so now this will have hoppings within and out of this unit cells. So for example, it will have hopping within. Okay, so let's say this is hopping strength is given by V, and it will have hoppings like between this inter unit cells. So let's call it W. Okay, and this all of these unit cells are indexed by some number, some integer, I minus 1, I plus 1, and so on and so forth. Okay, so let's see how do we write a tight binding model from this information. Okay, so Hamiltonian is basically an operator which has all of the processes that can happen. I mean, all of the hopping processes that can happen. Okay, so in that sense, in second quantization, when you write a Hamiltonian, it becomes very clear that what is happening inside the system, what kind of hoppings are are happening in the system. That becomes very clear in the second quantized thing. So let's call the red one to be A and the blue one to be B sublattice. So let's first write the intercell hopping. Okay, so the intercell hopping is given by C I A dagger C I B. Okay, and it has some energy V. Okay, and then there is the intercell hopping term, which is, for example, in this case, C I plus 1 A dagger C I B. Okay, and you just add Hermitian conjugate, and this is amplitude W. Okay, so now this is the Hamiltonian. So we can actually write this Hamiltonian real space, which becomes something like a tridiagonal matrix. Okay, and if you solve it, you will see that there will be some very, in some limit, you will see that there will be zero energy states. Okay, at the edge of the system. So so the limit is, I think, when W greater than V. Yeah, so when W will be greater than V, then you will see that there will be zero energy states which will be localized at the bulk, localized at the edges, and will be exponentially localized in the bulk. Okay, so but we are not actually going into discuss that, and these are some relevance in terms of topological insulators. So these are the edge states which are protected by topology, let's say. But so I think as the course will go on, you will learn some of these things. So but this is not the physics that we are trying to look into now. So for now, we actually want to derive the block Hamiltonian for this case, when this system has a two sublattice in an unit cell. Okay, so we'll see that what changes do we have to do in the previous kind of algorithm to get the block Hamiltonian. Okay, so here I'll have to define actually two of these operators, two Fourier series, Fourier transformations. See, so let's say J is given by 1 by square root n k c k a. Okay, so similarly I can also write for B as well. Okay, so now if you know the Fourier transform of the annihilation operators, you can also write the Fourier transform for the creation operators. Okay, so it is something like J a dagger is given by 1 by square root n and k e to the power I k j c k a. Okay, and similarly c j b dagger is given by 1 by square root 2 1 by square root n k e to the power minus I k j c k b dagger. Okay, so with that we'd like to put this Fourier transformations in the Hamiltonian. So let's just do that. So now H is given by V so by n, and so I'll use the dummy indices k1 and k2. So e to the power I k1 and to the power I k2 c k a dagger c k b. Okay, so yeah, so there will be j factor sitting here, right? Yeah, and so this is the interlayer, this is the intracell hopping term, and we have the intercell hopping term which will be w by n k1 k2 e to the power minus I k1 minus k2 j e to the power I k2. Okay, and then we write the operators, annihilation operators and annihilation creation operators. So k1 a dagger, k2 b. Okay, and there is Hermitian conjugate. So like we did in the last part, we'll actually use that definition of Kronecker delta. Okay, so we'll see that will give us k1 k2 v, that will give us delta k1 k2 . Similarly, in the next term also we'll have e to the power I k2. So let me just put this in bracket, and c k1 a c k2b. Okay, and there is a Hermitian conjugate part as well. Okay, so you can actually do a summation on this k1. So you are left with c, and then you can also rename k2 to be k. So you are left with v c k1 a dagger c k2 b plus w e to the power I k c k a. So yeah, it will just be k, and it will just be k c k b. Okay, and you have this Hermitian conjugate. So this is the block Hamiltonian. Okay, so now what we are interested in is okay, so this is H, and so whatever is in the summation is called the block Hamiltonian. So block Hamiltonian is the Hamiltonian momentum space. Okay, and so we can actually find the eigenvalues of the block Hamiltonian. So let's write HK. HK is nothing but CKA dagger CKV W e to the power I K CKA dagger CKB. Okay, plus Hermitian conjugate. So if you want to write this in the matrix form like we have done previously, so what we will do is we will actually write CK a dagger CKB in a row matrix and CKA and CKB in a column matrix. Okay, so and we will actually fill up this 2 cross 2 matrix. So this becomes 0 V plus W e to the power I K and V plus W e to the power minus I K. So this part is actually for the Hermitian conjugate part. Okay, so to diagonalize this, we'll have to diagonalize this Hamiltonian basically. So again, because this is a 2 cross 2 Hamiltonian, we'll again take the help of Pauli matrices. So let's first write this part. Okay, and then we have the off diagonal part, right? So the first part is quite okay, so it is just sigma x, but the off diagonal part we'll have to do a little more work there. W cos k W cos k 0 and plus 0 W sine k and I W minus I W sine k 0. Alright, so the first term is just V sigma x and the second term is W cos k sigma x, and then the second term, last term is W sine k sigma y. Okay, so we can actually pair up the first 2 terms and then we are left with the second term. So from this we can actually directly write the eigenvalues. Okay, so E of k plus minus is given by plus minus, so what it will be? It will be just V plus W cosine k whole square plus W sine k whole square. Okay, and there is square root. So we can actually simplify this thing a little bit. So it becomes 2V W cos k plus W square cos square k plus W square sine square k. Okay, so we can actually use the sine square plus cos square is equal to 1 identity in this place. Cos k plus W square. Okay, so this is what your dispersion will look like. So now we can ask that okay, so okay, how, I mean, what does the plot look like? So clearly we have two bands here. So initially we saw that when we have one particle in the particle in the unit cell, then we had only one bands. Now we have two particles in the unit cell, two sublattices in the unit cell. So then we get two bands. So this is actually a connection that is always there. So number of sublattice equals to number of bands in the momentum space. Okay, so I mean we can look at how what will be what the bands will look like. So let's say for some special points when k is equal to 0, then this E plus minus 0 is given by b square plus 2vw plus w square root. So it will be plus minus mod v plus w. Okay, so v is, let's say v and w is positive, or let's keep it a mod. Okay, at k is equal to pi, so E plus minus pi is given by plus minus v square plus, okay, not plus minus, 2vw plus w square. So then you get plus minus v minus w. Okay, and you will see that this is actually same for minus pi also. So let's also write plus minus pi. Okay, so now let's try to plot these two bands. So this is my k axis and this is my minus pi and pi. So again, so here I am assuming that lattice constant is actually 1, and I can actually so try to plot it. And I mean, assuming this unit is actually it is a simple thing. I mean, because it doesn't I mean fix any constant on the material itself, but it actually changes the momentum to be momentum by a in this kind of thing. Okay, so that's why it is kind of okay. So we have two bands. So at minus pi, so we see this is actually minus v minus w. So let's say this is v minus w mod, and this is v minus w mod. This is v minus w mod, and this is v minus w mod, and somewhere here we have v plus w. So what will happen is it will start from here, smoothly go to here. Similarly here also it will start from here, smoothly go to here. So here we see that so there are so this is the bandwidth. Okay, so this is a total bandwidth, but I mean you can look at the bandwidth of each of these things. So the bandwidth, so this is the bandwidth of the bands of the each of the bands. So it is given by v plus w mod minus yeah, so minus v minus w mod. Okay, so this is the bandwidth that we are looking at, and so this is a particle hole symmetric band. So whatever the upper band looks like, the lower band looks exactly opposite. So there is also chiral symmetry and particle hole symmetry, and also time reversal symmetry in this instance. So this is a very special kind of model. Okay, so we'll learn about symmetries as we go along in the course. So you can see that this is how the bands look like, and if you want to talk about the band gap, okay, so the band gap one has to also mention. So this is the band gap. So this is called the bandwidth. And this is called the band gap. So the band gap is what is the minimum amount of energy that I need to put in the system so that one particle from the lower band is excited on the other band. Okay, what is the minimum amount of energy for that? So which is called the band gap. So in this particular SSH model, the band gap is given by twice of v minus w mod. Okay, so actually something very interesting happens when v becomes w. So v is equal to w is interesting. So at v is equal to w, we see that the band gap actually vanishes. So let's actually plot what happens at v is equal to w. So this is minus v plus w mod. So something like that. I mean, the bands are supposed to be symmetric, but you can imagine they are. So this actually, so this is where the band gap closes, and this is referred to a point where there is a topological transition. So this is where the winding number of SSH actually changes from 1 or -1 to 0. Okay, so this will I mean, we can talk about it at some later point, but for now we'll actually just let's just focus on the bands. Okay, so I mean, this is all I had for today. So what we did today was we actually had a look onto some of the onto some concepts that we have done in the week 2. So let me just quickly go through again quickly go through what we have done. So we have actually looked into how to deal with Slater determinants. Okay, and then we have reminded ourselves how to do second quantization, and we have looked into some operators, for example kinetic energy operator, and charge density operator, spin density operator, and current density operator. So we have learned how does the time evolution happens in this system. So we have seen some simple example of how does one write the Green's function for a simple Hamiltonian. And we can also write how the tide binding Hamiltonians, how should the tide binding Hamiltonians be written for something like a special model, which is called a Schiffer-Heger model or SSH model, which is simplest one, the topological insulator. Okay, so all of these notes and videos are available to you, and you can check back. And if you have any questions, you can actually post in the Google group, so that some of the team member can actually answer that. So I'll see you again next week on the same time, and so you will have another session on Monday as well, for which you will get a reminder mail. Okay, so yeah, so then we should finish today, and thank you for listening.